It's You and Me, 9.5, Part 2, Convergent and Divergent series. All right, let's see. What if I asked you to do this forever? We have 5 plus 7 plus 9 plus 11 and then plus dot dot dot. Clearly it is an arithmetic series. You're adding 2 every single time to get the next number. But we've done it so that I've asked you for a certain finite series. What happens if I ask you to do it forever? Let's see. Let's go ahead and see what happens if I just ask you for the first 15 terms added together. All right, we've already done that. It is an arithmetic series. There's the formula. Here's the arithmetic sequence formula. These are the 2 arithmetic sequence and series formulas that you need. Let's go ahead and add up the first 15 terms. To do that, we're going to need this formula, the series one. We do know n to be 15. We know the first term. We actually don't know the 15th term. So let's fill all that in. So there's 15 is the n, but we don't know what the 15th term is, so we have to jump over this formula to plug everything in. We're looking for this. We know the first term. We know n is 15, and then we know the common difference is 2. All right, so plug everything in, solve it out. Now we know the 15th term is 33. We can take that and plug it into this formula. I know, formulas, plugging it in here, plugging it in there, there's a lot to work with. And then when you punch all of that into your calculator, we have, when you add all 15 terms up, we get 285. Let's do the same thing, but instead of just 15, let's take the first 100 terms and add them all up. See what that looks like. Go through the same process, put it into the series formula and the arithmetic sequence formula, and we would get 10,400. What if I asked you to do the first 500 terms? That's quite a lot. Do this whole thing, and you should get 252,000. So here's the question is, what if I asked you to keep doing this forever? What do you think the answer is going to be? Your guess might be infinity. The answer might go on forever. When that happens, we say that this series diverges to infinity, which means it just goes on forever, which kind of makes sense. If you add forever, your number is going to get bigger forever. All right, let's do another one just for fun. All right, let's look at this one. Let's see what's happening here. It looks like it's a geometric series. There's our geometric series formula. We know it's a geometric series because the r, it's important. What do we multiply to get to the next number? To get to the next number. Have you guessed it yet? R is 1/2. You're multiplying 1/2 every single time. All right, let's go ahead and just find the sum of the first 15 terms. We know what the first term is. We know R is now 1/2, and we're looking for the 15th, the sum of the 15 terms. So plug it in to that formula. Be careful when you put this into your calculator. Make sure you use PEMDAS, and make sure you use parentheses because it's very specific how you enter it into the calculator. But when you do it, you should get 9.9997. approximately. All right, let's do this again, but instead, let's go ahead and find the first 100 terms and then add them all up. Plug it all into the formula. It gets you 10. What if we do it for the first 500 terms? List out all 500 terms, add them all up. What do you think the answer is? Punch it in your calculator and see. What? How are you adding more and more and more terms, but when you add them, it's still 10? How does that make any sense? Just like the last example, the more you add, the higher the number is. But for this example, why is it that the more you add, it doesn't change? If I wanted to add the first 1,000 terms, it's still going to be 10. If I wanted to add for forever, this is still going to be 10. That is so weird. And so usually when we're in the classroom, I have an experiment or a demonstration actually. I'll have a student stand up and look at the door. So since we're distance learning, I want you guys to imagine standing up and looking at your door. Now, if I asked you to go ahead and go halfway to the door, so walk halfway to the door. Go ahead and imagine yourself walking halfway to the door. And then I said, from there, go ahead and walk halfway to the door again. So go ahead and walk halfway to the door. And then I said, walk halfway to the door again. And then walk halfway to the door again. And if I asked you forever to keep walking halfway to the door, are you ever going to reach the door? You might take tiny, tiny microscopic steps, but if I just say, don't go all the way to the door, I want you to go halfway to the door, you will never reach that door. And this is kind of what's happening here. And the key thing is this half, only halfway to the door. And it's not just half. Even if I said walk 1/3 way to the door, or 5/6 way to the door, you're never going to get to the door. And here's the theorem that states that. The convergent geometric series theorem. A geometric series converges if your r is in between 0 and 1. So basically it's a fraction between 0 and 1. Otherwise it diverges. All right, so the r is important. If I ask you to add forever, there's the first term, and then the r is the common ratio, but the common ratio has to be a fraction that's between 0 and 1. All right. If your r is bigger than 0, I mean, if your r is bigger than 1, then we say it diverges. So it also doesn't have an endpoint. So this only works if your r is a fraction between 0 and 1. All right. Let's do an example. Does this geometric series converge or diverge? If it converges, what number does it converge to? What's the door number? All right. It is a geometric series with r equals to negative 0.3. How did I do that? I just take this number, negative 4.5, and divide it by that number. And then you can do that whole thing. Take this number, divided by this number. Take this number, divided by this number, and all of them should be the same. They all should be negative 0.3. So negative 0.3 will converge because it's a fraction between 0 and 1. Absolute value. Plug it in. And it looks like The number that it'll never pass is about 11.5385. All right? Kind of weird, but that's the door that it'll never pass. Here's another example. Does this geometric series converge or diverge? R is negative 1.5. Again, if you need to know how to do that, you just take the second number, divide it by the first number, and then you keep doing that pattern. And you should get the same R every time. Absolute value is 1.5, which is bigger than 1, which means that this thing diverges. It doesn't have a door. All right. Last example for the day, repeating decimals. So we used to be able to use geometric series to write decimals as fractions. I mean, your fancy calculator does it for you. And I'll show you how to do it on the calculator as well. But here's how we change this repeating decimal, 0.432432 forever. This is how we change it to a fraction. If you notice, the decimal is the same thing as 0.432 plus 0.000432 plus 0.000000432, and that pattern goes on forever. And actually, we do know that this is geometric because it does have a common ratio. When you divide, you should get R equals 0.001. All right, and which means the 1 is a fraction that's between 0 and 1, so this does converge using the formula for forever. Plug it all in, simplify it. Well, when you have a decimal and a fraction, remember to make it no longer decimals, you move the decimal 3 places over to the top and to the bottom and reduce your fraction. And 16 over 37 is the fraction for this number. All right, so it's a complicated way of finding the fraction for this repeating decimal. You can also do it on your calculator. If you punch in 0.432432, and then there's a button that says math on it, the math button, the very first thing you see should be math frac. You should see the word frac, which stands for fraction. And so if you put fraction on that and then push enter, it'll actually give you the same answer, 16 over 37. All right, so the calculator will do it, but this is how we used to do it by hand. All right, go ahead and try the homework, see how well you guys do.